going. Okay, let's go ahead and get started. Veronica, Daniela, no Daniela, okay. William, Jack, no Jack, no. Okay, Gracie, Jacqueline, Melanie, Christopher, and Emmanuel, not here. Okay. So unfortunately I have to start with an apology to y'all. The quiz that I gave out on Friday was the incorrect version. It had the answers at the end. And so that was completely my fault. I got the quizzes mixed up when I was sending them out, and I didn't realize it until the end of the day. So I can't accept them as quiz grades, but I can accept them as something like extra credit. Okay, so I don't want to just completely get rid of that grade because I know plenty of y'all did real work on it, didn't even see the answers. Okay, so we're going to have another quiz Friday, and that quiz is going to be a lot of the same stuff that was on there, pretty much the same quiz, different order, different questions like values, and maybe one or two questions about standard deviation, which is what we're going to be going over today. Okay, so again, I apologize for that. That was completely my fault, and I've been trying to figure out all weekend what I'm going to do to fix it for y'all. Okay, let's go ahead and get into our lecture. So, what we have been talking about is measurements of location. So, where is most of our data located? Things like that. So we talked about mean, median, and mode, and we said that mean, median, and mode are all fairly good measurements of what our data is doing overall, depending on what our data set looks like. Now, there's another thing that we can use, and that is a standard deviation. So the basic idea behind a standard deviation is that if we have data that is distributed normally, remember that the middle part of this is the mean, median, and mode. Okay? So all three of those points fall right there in the center of our standard deviation. Our normal distribution. Now, what a standard deviation says is that if we analyze the data a little bit more and do a calculation on it, we can figure out the distance we have to go from this center point to enclose most of our data. So this would be one standard deviation on this side of our mean, and this would be another standard deviation on the other side of our mean. So one standard deviation of distance on each side. So remember that this is like a number line at the bottom here. Maybe this is 1 and this is something like 20. Okay, and then our mean and our median and mode and whatnot would be all right here in the center between 1 and 20. One standard deviation would be some amount of number. Okay, so maybe it's like 2. So we would count from the mean 2 spaces and we'd get our upper range. We'd count from the mean down 2 spaces and we'd get our lower range. And so this would give us the area that most of our data falls into. So instead of having just a straight one simple line number, like a mean, a median, or a mode, this gives us a range that most of our data falls into. And so this is a pretty accurate way to describe what our overall data actually looks like, is using this range of a standard deviation. So again, inside of this area right here, one standard deviation from the mean is where most of our data is going to fall. And so it's a pretty good description of what our data looks like, what the normal for our data is. Okay. So standard deviation is kind of like a mean, but it's like doing a mean twice. And the formula for it involves a lot of symbols. So before we get into the actual formula, I want to go over the symbols so that we're familiar with them. First is a symbol that we've seen before, and that's n. This is the number of data points we have in our set. Okay, so whatever data we have, we look at the number of data points we have, and that'll be our n. Next is uppercase sigma. Again, we've probably seen this one before. This is a Greek letter, again, sigma. And this is kind of like an operator. Just like we have add, subtract, multiply, divide, square, square root, those kind of things. Uppercase sigma is like those. What it says is get the sum of a certain amount of numbers. Okay? So it might ask us to do certain steps, and then once we've done those certain steps, we take a group of numbers and sum them together. Next one, x. X is just any data point. So if we look at a table of data, a lot of times you'll see the data labeled as X. Okay. So these are very common for a lot of the types of calculations that we do in sigma and, or uppercase sigma and x. Particular to standard deviation are the next ones. Now I've got to break this up real quick. Remember that we have populations and samples. What is a population? A whole thing. So if we were to take data for a population, we'd be taking data from everything in that particular group. So it might be everybody in this particular class, or everybody in all of my classes, or everybody at the university. Okay? What is a sample then? Part of it. So maybe I just pull like 3 people in this class, or 50 people in all my classes, or 100 people at the university. It's just a part of that entire thing. So when we are dealing with populations and samples, we actually have some different things that we need to take into account. And that goes along with some different calculations as well. First of all, for a population, the mean has a particular symbol. The mean is mu. Lowercase mu. And the standard deviation for a population is noted by lowercase sigma. Lowercase sigma is this circle with a like tail on top. In a sample, the mean is called x bar. It's x with a bar on top of it. And the standard deviation is noted by S. Okay? So again, we got some symbols here. N, just like we have used it before, is just the number of data points we have in our data set. Uppercase sigma tells us to take a group of numbers and add them all together, get their sum. X is just any particular data point we have in our set. When we're talking about populations, we use mu for our mean and lowercase sigma for our standard deviation. When we're talking about samples, we use x bar for our mean and s for our standard deviation. So let's actually look at the formulas for these. First of all, population standard deviation is lowercase sigma equals the square root of the sum of x minus mu squared over n. So what does this mean? Okay. So what this is telling us, step by step, is that we first need to find our mean. So if we're given a set of data and we want to find the standard deviation, we need to first find the mean of that set of data, mu. Then, for every single number in that set, we take that data point and subtract the mean. So each data point we have, we're going to plug in for x here, subtract the mean, see what we get. Okay? Then take all of those numbers that we got from subtracting x and mu, square them and add them up. So square them and add them up. And then divide by the number we have. So if you think about it, we get the mean, then we subtract it from x and square it, and then we add all of them up and then divide by n. Well, that's taking another mean, isn't it? Remember, to get mean, we add up all of our data points and divide by n. So we do that one time, and then we do it a second time with new numbers. Okay, so essentially taking a standard deviation is like taking a mean twice. There's just a little extra step thrown in there. Sample standard deviation is actually calculated a little bit differently. For the most part, it's the same though. So sample standard deviation, S, equals the square root of the sum, sigma, of x minus x bar. Again, that's just the name for mean in a sample, squared, over n minus 1. Why do you think we would use n minus 1 for our sample standard deviation? What's different here between a sample and a population? We don't have the whole group, yeah. A sample does not represent the entire group. It's an approximation. So the reason we have n minus 1 here is to take that approximation into account. We don't have the whole n. We have something close to the n. It's a sample. Population, we've got the entire n. We know everybody in that entire group. That's why we have n. Does this make sense? Any questions? Okay. So let's go ahead and try this out. First, let's try out a population standard deviation. So once again, our formula for a population is sigma equals the square root of the sum of x minus mu squared over n. So let's get some data to do this with. I've got an example here that I pulled from online, and it says you and your friends have just measured the heights of your dogs in millimeters. Okay. So if we want to know what most of these dogs look like, we'd want to find the standard deviation. So we can get a range of heights that the normal dog would fit into. Okay? Now it's a population because we're not talking about all dogs, we're talking about just the dogs in this group of friends. So this is a population. Okay? So the heights are measured from the paw to the top of the shoulder in millimeters. They are 600 millimeters, 470 millimeters, 170 millimeters, 430 millimeters, and 300 millimeters. Okay. So, again, we want to find the standard deviation. And to do that, we need to first know the mean. So how do we find mean? Do what? Add them all up and divide by n. So we could say that mu equals the sum sigma of x over n. Okay, so let's go ahead and do that. Find our mean. So 600 plus 470 plus 170 plus 430 plus 300. We get 1,970, and we need to divide by the number of data points we have, so divide by 5. And we get 394. So our mean, is 394. Okay. So now, in order to find our standard deviation, we need to take this part, x minus mu, and figure out those numbers. So we need to take each of these data points and subtract mu. So like 600 minus this, 470 minus this, so on and so forth through all of our data. So let's figure out what that is. 600 minus 394 is 206. Okay. 470 minus 394 is 76. 170 minus 394 is negative 224. Uh, 430 minus 394 gives us 36. And 300 minus 394 is, of course, negative 94. Okay. So we've got our x minus mu numbers now. Okay. So essentially we've done what's in the parentheses. Now we move on to our next step in the order of operations, which is exponents. We need to take each of these and square them. So, let's see here. If we square them, this will be x minus mu squared, we get 42,436. 5,776. 50,176. 1,296. And 8,836. Now I want you to notice something about these new numbers. When we did x minus mu, some of these came out to be negative. But when we squared them, that gets rid of that negative. Remember that a negative times a negative, in other words, squaring, makes a positive. Okay? So why do we square them? That is because negatives would cancel out our positives. We wouldn't be getting a sum anymore once we start adding all these up. We'd be getting a difference. We want to make sure that we're getting a sum for this basically mean standard deviation. Okay? So now we need to do our sum of x minus mu squared. So we're going to take all these numbers and add them up. And I've got that written down here. Add all these numbers up, we get 108,520. So next step, we need to divide by the number of data points we have. So divide by n. Oops. So minus mu squared over n. So again, take this and divide it by how many we have. So how many data points do we have? 5. So we're going to divide 108,520 by 5, and that's going to give us, let's see, 21,704. And one more step. We need to take the square root of that. So take the square root. So if we take the square root of that, we get 147 point something something something, but we want whole millimeters, so we're just going to round to the nearest millimeter. So 147. And there is our standard deviation. We've done every step in our formula, so we've got our value. Does that make sense? Okay, so what we can say about our heights of our dogs here. Okay. Again, the mean was 394, right? We calculated our mean, our average, and we got 394, and that's going to be right here. Now, again, that's the average. Most dogs are going to be somewhere around 394 millimeters. But where around them, that's our standard deviation. So our standard deviation, if we go 147 points in this direction and 147 points in this direction. So let's see, 394 minus 147. So one standard deviation in this direction, again, we're going from 394 down 147 points, so that gives us 247. And then from 394 up 147 points, that's 541. So one standard deviation back, one standard deviation forward. Between these 2 points is where most dogs fall in this group. They're going to be somewhere between, usually somewhere between 247 millimeters and 541 millimeters. Okay? But of course, that's most of them. Not all of them fall in there. You have things like Dachshunds, wiener dogs, that are really, really short dogs. they're going to fall somewhere over here in the really short category. Great Danes or Irish Wolfhounds or something like that, they're really, really tall dogs, and they're going to be over on this side. Okay? But again, most dogs in this group are going to fall into this range right here between 247 millimeters and 541. Any questions? No? Makes sense? Good. Okay. So once again, this is a population mean. It is only slightly different from a sample mean. So let's try sample mean as well. And I found a example online that gives us some pretty simple numbers to work with. Okay, so again, sample mean, S, is the square root of the sum of x minus x bar. Remember, x bar is the symbol for mean in a sample, squared over n minus 1. That's the important part there, is that sample has not n, but n minus 1. All right. And again, x bar, just like mu, is sum of all points over n. All right, so let's get some data in here. This says a sample of 4 students was taken to see how many pencils they were carrying. Okay, so this is a sample, not a population, but a sample. So we want to take the students that we polled and project it to what we would expect the rest of the population to look like. So even though we're just taking a few of them, we're using this calculation to project it to everybody else. That's what a sample is doing. So one of them had 2 pencils, 5 pencils, and another one had 7 pencils. Okay. So just like before, the first thing we need to know is that mean, x bar. So we need to add all these up and divide by n. So 2 plus 2 plus 5 plus 7. Let's see, 2 plus 2 is 4. 4 plus 5 is 9. 9 plus 7 is 16. And then we have 4 data points. So 16 divided by 4 is what? 4. So our x bar is 4. Our mean is 4. Okay? So next, going from x bar, we have x minus x bar. So we need to do each of these data points minus our mean. Okay? So let's go ahead and figure that out. Well, let's see, 2 minus 4 is what? Negative 2. 2 minus 4 is again negative 2. 5 minus 4. And 7 minus 4, 3. Okay, so those are x minus mean. Now we need our x minus mean, what? Squared. So we're going to square all these numbers. So negative 2 squared is what? Positive 1 squared? 1. 3 squared? Okay. Next, what do we need to do with all these numbers? add them. So we're going to get our sum of x minus x bar squared. So sum these numbers up. 4 plus 4 is 8, plus 1 is 9, plus 9 is 18. Okay, good. So we've gotten our mean, we've subtracted x minus mean, we've done the square, we've done the sum. What do we need to do now? Do what? Divide by n minus 1. Good. So sigma of x minus x bar squared over n minus 1. So what is our n? 4, so minus 1 would be 3. What? Yeah. Yeah, so n is 4, minus 1 would be 3. So we need to take 18 and divide it by 3. What is 18 divided by 3? 6. And are we done yet? No, what else do we need to do? Square root the whole thing. So square root of sigma x minus x bar squared over n minus 1. Let's see. Square root of 6 is 2.4494. We're going to round this. If we're talking about pencils, we really ought to round to the nearest whole number, shouldn't we? So let's round this to 2. Okay. So our standard deviation here, again, if we were to lay this out on a normal distribution, right here in the middle is 4. Again, that's our mean. Our standard deviation is 2, so to find the lower boundary, we go down 2. So 4 minus 2 is 2. To find the upper boundary, we add 2. So 4 plus 2 is 6. So 1 standard deviation down, 1 standard deviation up. This is where most of our data will fall, somewhere between 2 and 6. Of course, some students will only have 0 or 1 pencils, or maybe half a pencil if they're really unlucky. So they're going to be down here, outside of most typical students. Some students are going to have more than 6, but not a lot of them. Again, remember that the curve here, the height of the curve, shows more and more data represented. So more and more students with these pencils here. So most students are going to have 4. But within a standard deviation of that, somewhere around 70% of our data, 70 or 80% of our data is going to be, they either have 2 to 6 pencils. Again, this range is a broader interpretation of our normal looking data, what would be considered normal for this set of data. So it would be considered normal for how many pencils? 2 to 6 pencils. Any questions? No? Makes sense? Excellent. Cool. Okay, then I believe that will do it for today. So again, I'm sorry about what happened with the quiz. We'll just have to try to make that up on Friday. But I'll see y'all on Wednesday. I hope you have a good day.